Thank you. While the things are setting up, welcome again to the second and the third lecture of Biomaterial Science course. Today we are going to talk about mechanical properties, and it's my absolute pleasure to have Dr. Alex Falk. I couldn't think of anybody better than him to give this lecture. He is a mechanical engineer by training, so who else to give that lecture to you? He has a PhD in mechanical engineering from University of Manchester, and he has been with the center for more than 15 years. He's the director of MDRCBB, which is Minnesota Dental Research Center for Biomaterials and Biomechanics, and also the division director for biomaterials, which is part of restorative sciences. So without taking any further of your time and his time, I'll let him take over the class. It's all yours.
Oh, thanks, Isha. Yeah.
Thank you.
Good morning, everyone. Okay, you recovered from yesterday? Well, I was here working on the slides, so you can have them last night. Yeah. Okay, right. So I'm an engineer, not a dentist, so you don't have to listen to me, but I'm sure you have to pass your test, so maybe you need to pay attention, okay? So the aim of these double lectures is to empower you with knowledge so you can pick the right materials for your restorations when you graduate and become a dentist, so that we have longer lasting restorations. So obviously mechanical properties are important. Why are they important? First of all, as I said, they allow you to select the right materials. You need to know whether metal, ceramics, or resin composite is the right one for the restorations that you are going to prepare. And they would determine the design of those restorations or prostheses. As I'm going to give you some examples later on. And ultimately, they will determine how well your restoration is going to perform clinically. Okay? Yeah? Has any one of you seen this life cycle of a tooth? Okay? Well, you will see it if you become a dentist. So it'll start with some sort of sealant, okay, to protect the surfaces of the tooth. But eventually, for some of us at least, who do not pay attention to hygiene, you're going to develop some caries, and it will not be reversible. You're going to have to excavate those carious tissues and put on the restorations. Unfortunately, right now, those restorations don't last very long. If you believe the literature, they have an average life, at least for resin composite restorations, about 6 years. Okay? So on average, every 6 years, you're going to have to dig it out, make a bigger hole, and then put in the bigger restorations. And the cycles continue until you have removed so much tooth tissues that you're going to impact the pulp. Okay? You're going to need endodontic treatment. And after that, perhaps the tooth will crack, and then you have to replace it with an implant. So your job as a dentist is to prolong that cycle as much as possible, okay? Implants are expensive. Not everyone can afford it, yeah? And it's very intrusive. So the longer you can preserve a tooth, the better. Okay, I said you can do better, not we, because I'm not a dentist, okay? You can do better, right? So there's an article published a few years back on the clinical studies of the performance of resin composites. If you read the highlighted text, it says after 2 years, the estimated annual failure rate was 7.8%. So after 2 years, about 8% of those restorations would have failed, okay? And usually the failure rate would keep on increasing. So in your third and fourth year, there could be 10, 15%. Of the remaining restorations that would fail. All right, I'm going to make a little digression since I'm an engineer, right? I love engineering structures. So on the left, you have one of the oldest stone arch bridge in the world. I think it was in Scotland. Okay? Obviously, it's built of stone. Now, stone is weak in tension, but incredibly strong in compression. So that's why you have that arch shape, right? But since we discovered metal, we can build stronger, bigger bridges, right? You're going to have to build some bridges in your career, like the one there at the bottom right. It's a 3-unit bridge. In the past, they were made of metals, but these days we're moving towards ceramics. And the discovery of metals can actually turn some of our designs on their heads. Any Egyptians here? No? Okay. Well, if you are, you should be proud of the pyramids. They're also built of stones, right? It's optimized, okay? It's wide at the base because stones, again, can take on a lot of compression, right? They can't take on tension. But with the right design, a structure can last for hundreds, thousands, or even longer, okay? And with metals, we can actually turn the pyramid design upside down, yeah? Okay. So you can chew with your pyramids, okay? Just like your cuss tips. Right, so as I mentioned, in dentistry, for the sake of aesthetics, we all want to look beautiful. We don't want ugly, metallic-looking restorations in our mouth, not anymore. So we are moving away from metals in many cases to ceramics, okay? But as you know, ceramics are brittle. They tend to chip, if not crack. So when you prepare ceramic crowns, you're going to have to make it thicker, yeah? Okay, it cannot be as thin as metals. So what's the impact on the tooth that you're going to have to prepare? You have to remove more tooth tissues, right? Okay, you have to be careful so that you don't get into the pulp, right? Because the consequences, as you know, is dire. Right. So we've been talking about materials, but as an engineer, I always say dentists are engineers. You just don't know it, okay? When I say that to my dental friends, they will say, no, we're also artists. All right, okay. You're an architect, right? But apart from materials, you also need to consider geometry, yeah? Shape, size, etc. We've just talked about the importance of a thickness of a ceramic crown. You also have to know the loads, right? Is it anterior or posterior? For anterior teeth, you have a lot of shear force in addition to just a lot of compression force, okay? And materials behave differently under different forces. You can adjust your occlusion, so you can eliminate contact, so the teeth never come into contact, and your restoration will last forever. But then your patients will not be chewing very effectively, right? Okay, so bear in mind those 3 important elements when you become a practicing dentist. It's not just about aesthetics, making a beautifully looking restorations. They've got to work and they've got to last, right? I'm paying $200, $300 for a resin composite restoration. Maybe more these days, I don't know. Okay. If I have to come back in 2 years' time, I'm not going to be a very happy customer, am I? Right? Okay. So moving on. Okay. We know the importance of mechanical properties. How are we going to measure it, right? Or what's the point of measuring those properties? The first one is to characterize the material, okay, using fundamental properties, and I'll tell you what these are. So in the process, we can determine whether this is stiff or a flexible material, okay? A restoration doesn't just have to produce the right forces, okay? It needs to have the right deformation too. Now, rubber is very tough. Okay? It's very hard to break a piece of rubber, but obviously you don't want to put a piece of rubber as a restoration in your mouth because there's just too much deformation. All right, okay? It's good as a tire, okay? But it's not good as a restoration, right? We've mentioned metals and ceramics, the contrast between ductility and brittleness. Right, well, once we know the fundamental properties of those materials, we want to use them to predict what sort of stresses or strains there are in the restorations under the clinical situations, right? Okay. So that we can assess the risk of failure, right? How far are we from the breaking stress if I have a restoration of such a design made of such a material? Yeah? Or what is the deformation, okay, in that bridge? Is it going to impact on the underlying tooth tissues? Yeah? Or for a denture, okay? You need to make sure that it's stiff enough so when the patients wear it, it's going to have the right occlusions and have the right comfort, okay? Once you know all this, then you can determine how long your restoration is probably going to last, yeah? Then you can charge your customer accordingly, okay? When you go to buy a car, similarly, you want to know how robust your Toyota or whatever, okay, is going to last. Is it worth paying that sum of money? Okay, well, a bit of classifications of mechanical properties. First of all, you can separate them into bulk or surfaces or surface properties. Now, bulk properties I consider fundamental or independent. So you take a lumber material, you put a load on, you get a single value, okay? Yeah? It doesn't depend on anything else. Now, surface properties tend to be compound or dependent. For example, friction, yeah? It doesn't just depend on the materials, it also depends on the opposing material, okay? The roughness, the surface roughness of your sample, whether there's any lubrication. Hardness is another one. As you see, it depends on the stiffness of the material as well as the plasticity. Okay? Any questions so far? Good. Right, for bulk properties, you can also classify them into static or dynamic. It really depends on how you load it, okay? For static properties, you increase the load steadily, okay? So inertia doesn't come into the equation. For dynamic properties, you can change the rate of your loading. You can make it cyclic instead of monotonically increasing. And some of these properties also depend on the viscous nature of the materials. And I'll go into a bit more details of each of those. So, okay, I have mentioned stress and strain, okay? I'm always under stress because of the work, but that's not the sort of stress I'm talking about. These are physical stresses, and the definition is force per unit area, okay? And for stress, we're talking about internal, yeah? Okay. I need 3 volunteers, okay, to do a demonstration. Come on, join me up here. Yeah, come down here. 2 more. Yep. Great. What's your name? Tony. Tony. Okay. And you? Gailey. Yeah. And you're Billy? Huh? We, okay. I want you to form a chain, yeah. Okay. So Gady, stay where you are. Yeah, yeah. Okay, right. I'm going to pull on them, right? Okay. I'm applying a force. Okay, this is the external force. Can you feel the force? Not yet, right? Can you feel it now? Yeah. Right, okay. You can't see it, but it's there, right? That's the internal force, and that's the stress. Okay, very good. Thank you. All right. Okay, well, the reason why we consider force per unit area is to get an average intensity so we can compare between different situations. So it's like comparing the wealth between America and a small country like Belgium, right? How do you compare, right? You divide it by the number of population, yeah, number of people. So in the same way, to compare stress or force, we divide the total force by the cross-sectional area that the force is acting on. Right, so here you are, cylindrical material under tension, okay? And the force is F, the cross-sectional area is A, so the stress is F divided by A. And the unit can be, pound per square inch, I almost forgot that one. Yeah, kilogram force per centimeter squared, or Pascal, Newton per meter squared, or Newton per millimeter squared, or megapascal, gigapascal, okay? Depending on whether you're looking at big stress or large stress. SI system is always preferred, yeah? There's been some disaster mixing units. A few years back, they were sending a very expensive satellite to Mars or somewhere, and the components were built by different people. Some were built by Americans, some were built by the British. And because of the mix-up in the units, those components do not match. So we just wasted $1 billion or something. Okay, so getting the right units is important, all right? Types of stressors, you have already seen tension, okay? You failed the tension, yeah, right? But I can also push, okay, to create compression. Typical example is an implant or the natural teeth. They're always under compression. But the moment you replace a missing tooth with a bridge, or you build a bridge on an implant, when you load on the, what do you call that? The cantilever bridge, yeah. Okay? You're going to create a shear force, right? Okay? The implant is still going to give you a vertical force, but there's a separation of those two forces in terms of distance. So whenever you have a separation between the two forces, you're going to create a shear, okay? Those two components, the implant and your bridge, are moving in different directions, okay? And tension and compression are called direct or normal stresses. The shear is shear. Right, in reality, stresses are very complicated. The simplest example is a beam in bending. So if you take a piece of rubber and you try to bend it, the top surface will be in compression, okay? It's shortening, whereas the lower surface is in tension, okay? It's lengthening, right? And for a configuration like this, which is called three-point bending, 2 supporting point, 1 loading point, the greatest stress, tensile stress at least, it's at the midpoint of your beam and on the bottom surface, okay? Now that's a regular beam. Now when you have a bridge, a dental bridge, like the one on the right, where the geometry is really, really complicated, right? The stresses will not necessarily be at the bottom of the bridge, right? You tend to be at the sections with the smallest dimension, okay? Right? The proximal region. right? Um, we've seen shear stress. The shear stress can also exist in something under torsion, okay, or rotation, like an endodontic file, okay? Yeah? So neighboring faces are doing this, okay? They are not extending or being compressed. They are rotating relative to each other. So they are under shear. And for a circular cross-section, the maximum value is on the surface, okay? Because on the surface, that's where the maximum displacement occurs. Near the center, the relative motion is the smallest, okay? Right? So if an endodontic file is going to fail, where is it going to start failing? It will start from the surface, right? So that's why sometimes you can do chemistry on the surface to make it stronger, all right? Okay, we have already mentioned the effect of irregular geometry on the stress distribution. So whenever you take out material, okay, like making a hole in your teeth, okay, the cavity prep, the neighboring remaining material will have to take up more load, okay? You're missing your partner next to you. No one's going to share the work, so you have to take up more work, right? So whenever you have a discontinuity in geometry, you're going to have so-called stress concentrations. Those local area we have to take up more force, okay? So remember, stress is force divided by area. You have a smaller area, same force, so there will be an increase in stress intensity, right? And the important thing to recognize is that most failure, as we mentioned, would start from stress concentrations, okay? So on the top left, that's a computer simulation of a class 1 restoration under occlusal loading. It's an amalgam restoration, by the way, because amalgam is not bonded to the surface, so we can just take it out from our model and just look at the remaining tooth in isolation. The colors represent the level of stresses. So red is the highest, blue is the lowest. And as you can see, the position of those red dots, they coincide very well with the fracture point clinically. Okay? So this is not by coincidence. Okay? This shows you engineering works. Okay. In the middle, we have an implant. Again, you can see those stress concentration areas. Now, the stresses don't exist just in the implants. Okay? The implant doesn't exist in isolation. Okay? It's connected to the neighboring tooth tissues, your bone. And the loading can also create stress concentrations in the bone. Yeah? So that's why you can see a lot of bone resorption in the first couple of years when you put an implant in. Yeah? For brittle materials like ceramic and glasses, because they are brittle, they are especially sensitive or vulnerable to any stress concentrations. And this could happen at a very small scale. So any scratches, surface roughness, will introduce tiny stress concentrations, but high enough to cause crack initiation and propagation. So chipping from scratches is quite common in ceramic restorations. How are we doing with time? Okay. Right. We've just talked about stresses. What about strain? So this is like average deformation. Yeah? When you pull on something, it's going to get longer, right? But for ease of comparison, right? If you pull on a long rod compared to a short one with the same force, you're going to get different elongation, right? You're going to get more deformation when you pull on a long rod, okay? Smaller deformation from a shorter rod with the same force, yeah? Okay. But you can spread those deformation along the entire length of your component so that you can compare them on a more equal basis. So strain is your average elongation over the original length. And because you are dividing a length by another length, there's no dimensions. Okay? There's no unit, unlike stress. So strain is dimensionless. And as I said, is a measure of the average elongation or compression or skewered, if it's shear. So you can compare different components on a more equal basis. Right, so here's an example. You've got a nose there already, right? Okay, so if the original length is 100, whatever unit it is, I don't really care, because strain is dimensionless, right? And it's stretched to 102 units. So the change or increase in length is 2. So the strain is just 2 over 100, i.e. 0.02 or 2% strain. Okay? So strains are usually expressed in percentages. Right, so similar to stresses, you can have tensile strain, compressive strain, or shear strain. Okay? So when the shear strain is small, you can work out its value through its angular displacement. Yeah? So at the top, we have a skewered or displacement of W. That needs to be spread over the entire length of your sample. So the average shear strain is just W over L. And when it's small enough, it just happens to equal to the angle of that displacement. Okay, I was going to bring a paper clip, but I forgot. Okay, anyone's got a paper clip? No, okay. I forgot we're in 2024, right? It's all paperless now. Okay, but if you have a paper clip and you bend it by a small amount, it's going to spring back, right? But if you bend it, okay, really well, right, you're going to create so-called permanent deformation, yielding, plasticity, etc. So strains can be divided into 2 types, okay? Temporary or recoverable or elastic. So you can recover the entire strain by just removing the load. If the load is too large, then you're going to create permanent or plastic strain, okay? So when you remove the force, the displacement would remain, okay? That's just everyday experience, right? So here's a very nice example of the importance of having the right strain at the right time, yeah? Have you all done impressions? Not yet? Okay, well, you will get to practice on each other. Hopefully your partner will do a good job. Okay, it's not a very nice experience because they don't smell very nice. Yeah, they taste bad. Okay, so you have to mix up these chemicals. Yeah, as a polymer. Before it's set, okay, you have to insert it to the mouth and ask your patients to bite on it quickly. Yeah, and that's going to stay there for a while for it to set. And then after setting, you need to pull it off. Hopefully you can do that easily, okay? So during the insertion, you need to make sure the material is behaving plastically, yeah? You can fill up all the gaps, all the proximal areas, okay, to get a true impression of the material, right? But when you pull it out, okay, because of the undercut, the material needs to expand, okay, to get out. And you want that expansion to be elastic, okay? So when you remove the force, it will spring back to the right position, okay? So that's a very good example of when and where to have plasticity and when and where to have elasticity. Yes? it's elastic because when you pull it out, it needs to deform, right? Because they are undercuts, yeah? When the material conform, you know, to the positions underneath the crown, okay? So you need to deform it to get your impression out, okay? And it needs to be elastic to spring it back, okay? Yeah, yes?
So basically what you're saying is you can't permanently change it once it's cured.
Once it's cured, yes, that's right, okay? All the permanent deformation is so small that it doesn't matter, okay? Because you can never 100% cure a material. There will always be some uncured material in it, okay? Right. But as long as that deformation is small enough, okay, the patients can't detect it, yeah, they can't tell the difference, then it's okay, yeah. But apparently, our tongue and soft tissues are very sensitive. Anything bigger than 1 micron, we can tell the difference, okay? Right. The plastic strains are usually undesirable, especially when you have restorations, because, as I said, the patient's mouth is so sensitive, so any permanent deformation, they will be able to detect it. So if you overload an implant, okay, and you cause permanent deformation, your occlusion, okay, would not be very well. Okay? The teeth are not very well aligned, all right? So to avoid that, you should select a strong enough materials with high enough yield strength, or you use a very robust designs. Make sure that all the cross sections are thick enough so the stress level remain acceptable. Or, as I mentioned, you can adjust occlusion, so you can lessen the load on your restorations. So, what am I talking about here? Remember the design triangle? Okay? Materials, geometry, and loads. Okay? They are all connected. One will impact on the other. Okay, right, so I've defined stress and strain, and you've seen a demonstration. When you put on something, they will change in shape or form. So how are the two linked together? Right, it's material dependent. If you have a soft material, you apply a force, you're going to get more deformation. If you have a stiff material, you apply the same force, you're not going to get as much deformation. If it's a metal, you're going to get a very different stress strain curve, as I'm going to show you, compared to a brittle materials, which produce a lot more simpler stress strain curve. So anyway, you have to start out with some sample. If we are talking about metals, usually you would create a so-called dot bone specimens. Okay, so these are either cylindrical or rectangular in cross-section with bigger dimensions at the end for you to grip onto, right? Okay, and the central test section is usually smaller, so you can concentrate, remember stress concentration? You can concentrate the stresses along the central thinner section so you can examine everything within that section. Usually you would do a pull rather than a compression because it's much easier to ensure things are sort of aligned in tension than in compression. When you apply compression, things can sort of tilt, right? So the basic stress strain curve is usually done with tension. And when you do that, the machine will measure the force and the elongation. And from that, you can determine the stress and calculate the strain. And you plot one against each other. And if you do that, the first thing you will see is a linear relationship. Okay? So from point O to A, you have a straight line. And that's called the Hooke's law. Hooke was a contemporary of Newton. He did a lot of fundamental work on the mechanical behavior of material. Okay, and simple analog would be a linear spring. Okay, you apply a force, you can extend it. You apply twice the force, it will extend twice as much. So within that elastic, linear region, beg your pardon, because sometimes you can confuse elastic with linear. Within that linear region, force or stress is proportionate to strain. And the slope, okay, of that linear relationship is called the modulus of elasticity or Young's modulus. So it defines the stiffness of the material. So the steeper the slope, okay, the more force you need to create a particular strain. Okay? So the material is stiffer. If you have a low slope, you don't need as much force or stress to create the same amount of strain. So the material is more flexible. Okay? So it's a property that engineers use a lot. Okay? Everything is about forces. Yes? That's right, yes. So we go back, okay? A steeper slope means you need a greater stress to produce the same amount of strain, okay? So it's stiffer. Right, if you continue to load your dog bone specimens, you're going to reach a point, B, where the slope is no longer constant, okay? Yeah? You get a little curvature, right? But as long as you don't go past point B, the behavior is still elastic, meaning when you remove the load, you're still going to get back to the original point, okay? You can recover the entire displacement, okay? It's nonlinear, but it's still elastic, yeah? But within the linear portion, it's also elastic, okay? Right? It's a bit subtle, okay? I know that, yeah, because I went through the same thing, yeah. I always thought nonlinearity is in elasticity, but it's not the case, yeah. So you can have nonlinear but still elastic behavior. But if you go beyond point B, you're going to have permanent plastic deformation. When you remove the load, okay, your curve is not going back to the origin, yeah? So when you remove the load from somewhere between B and C, your curve is going to go to a point somewhere like here. Okay? You're going to have a permanent deformation, yeah? And point B is called the elastic limit for obvious reason. And point A is the proportionality limit. Yeah. Now, if you reach a point like C, then you don't have to increase your force much to get a lot more permanent deformation. Okay? So point C is called the yield point. Okay? So that's the point most important to engineers. We always try to design using the yield stress. We want to make sure every component, or all the stresses in every component, do not reach their yield stress. Okay? Then your structure would be safe. Yeah? Because we know that once you remove the load, we're going to recover all the deformation. Yeah? Okay, I've used a linear spring as an analog for the proportional region. When you have permanent deformation, we can use a frictional element as an analog for the stress-strain behavior, right? Well, I hope you know about friction. Yes? Okay, it's proportional to the reaction force, okay, acting on the surface with the frictional coefficient. Yes? Okay. Now, to move something against friction, you have to apply a high enough force to cause permanent displacement. Okay, I'm trying to move my water bottle here. Okay, right. I have to build up the force high enough to overcome the frictional force between the bottle and the tabletop. So if I manage to do that, I'll be able to create a permanent deformation. Okay? So it's a nice, simple analog to describe what permanent deformation is. So we have spring and a frictional element. All right. So you can keep on increasing the load, and eventually something has to give. Okay. So there are a few terms that you need to be aware of. One is the ultimate strength, and the other is the maximum strength. You would have thought, well, the maximum strength should be equal to the ultimate strength, but that's not necessarily the case. And if we go to the entire stress strain curve, you will see why. Because at some point, okay, you're going to reach a maximum. That's the maximum strength. You can continue to increase the elongation or lengthening of the component without increasing the force. Actually, the force is reducing. Okay. Does anyone know why? Have you heard of necking? I don't mean necking with your girlfriend or boyfriend. It means that under plastic deformation, the cross-sectional area is reducing. You're forming a neck. All right? Because the cross-sectional area is reducing, the effective stress is actually increasing. Okay? But the stress strain curve is constructed by using the original dimension. Okay? If you replot this using the current cross-sectional area, you will see that the curve continues to increase. Okay? Right. So you're right. The ultimate strength, if you determine it that way, will be higher than the maximum strength at this point. Okay? Yeah. Well, at least I get a laugh from you, necking. Yeah. Okay. We'll carry on for a bit more before we take a break. Okay, ductility and malleability. Well, these are more or less the same thing as a description of how plastic a material is, but ductility is in tension, is for tension, whereas malleability is for compression. So a material is ductile if you can pull it, okay, and create lots of permanent deformation. And the material is malleable if you can compress it quite easily to form into the shape that you need. And both of these are measured by percentage of deformation. So I have already shown you what elongation is. So that's the strain at the point of breaking. In practice, okay, you have to define some sort of gauge length in your dot bone specimen. And depending on the gauge length that you define, you're going to get different elongation. All right? So when you report elongation, make sure you report your gauge length that you use for measuring that as well. Okay. Right. I'll cover the next two slides, and then we'll take a break. How's that? Okay. So far, we've only looked at discrete points or sections along the stress strain curve. We have looked at the proportionality limit. We have looked at the elastic limit and the yield point. Okay. We've looked at elongation. So these are all discrete points along the stress strain curve. But we can also characterize the material by looking at the area underneath the curve. Okay? The discrete points give you stress and strain. The area underneath the curve gives you energy. Okay? Is the integration or the multiplication of force and displacement, and that's energy. It just happens that the unit comes out as energy per unit volume of material. Okay? So if we look at the area underneath point B, okay? If you remember, beyond point B, you're going to get permanent deformation. So the area underneath point B is the energy required to cause permanent deformation. And that's defined as the resilience of your material. At the final strength, we have fracture. Okay? So if we take the total area underneath that curve, it would be the energy required to separate the material. And that's called toughness. Okay? Resilience and toughness. They're both measures of energy required to cause permanent damage or fracture of the material. Yes?
Can you define resilience as the elastic or to reach past the elastic then?
Yes, that would be the case.
Okay.
Yes. Yeah. So when you reach the elastic limit, that means you can get permanent or plastic deformation. Okay? Well, let's take a break there. I'll see you back at whenever. Yeah.
Dr. Fox.
Yep. Hi.
So, quick question. So I was a little bit inspired by the, or not the, actually I'll let you ask it. I forgot it.
Could you kind of explain the necking again? I kind of
Oh.
lost focus at a point.
Well, there's your necking.
Oh, okay, awesome,
All right?
sweet. And my question.
Because under plastic deformation, volume is conserved.
Okay.
Yeah? Okay?
Yep. Oh yeah.
So when you increase the dimension in one direction, you're going to have to reduce dimension in the other direction. So that's why you get thinner sections.
Oh, so physically. Okay. And for the when you're measuring ductility, are you measuring the elongation at maximum strength?
No,
or
at
are
the
you measuring
final.
at the final?
Yeah.
Okay, awesome.
Okay.
Thank you very much.
All right. Yes?
When you were talking about like the ultimate strength, so you're saying that this one is higher than the maximum strength because if the area was the same, go
Yeah.
linear?
Okay? That's necking. Okay? Because the cross-sectional area reduces, the stress, the actual stress, the real stress would be much higher than what is depicted
Then
there.
what is depicted? Okay.
Because that was calculated using the original
Okay.
cross-section.
Got it. Okay. Yeah, that makes
All right?
sense. Thank
Okay.
you.
Yep. Yep.
So when a material breaks, so I'm just kind of trying to understand, like, why does it like go down? Is it kind of like taking silicone and kind of as it gets longer and longer, it becomes easier to pull apart? Is that why?
Yeah, because you have necking.
Yes.
Okay.
Okay.
Yeah, the cross-section area is smaller.
So
So
it
you
takes
need a
less
smaller
end.
force
Oh.
to keep on
okay.
increasing the length. But it doesn't mean that the stress is reducing. The stress is actually going up because of the reduction in the area. Right? It's force per unit area.
Ah. Okay.
Okay? So the actual stress strain curve, if you use the actual area, will keep on going up.
So to keep going on, it'd
Yeah.
still be a little bit more linear.
It won't be linear.
Okay.
Yeah, it's non-linear.
Okay.
Okay, but it will not be decreasing.
Okay.
Okay? It's decreasing purely because we are using the original cross-sectional area to calculate the stress.
Okay. The thinner. Oh. Okay.
Right.
That makes sense.
If you account for the reduction in the cross-sectional area,
Then it would
the
keep
curve will be going up.
Okay. Thank you.
Okay? Yes? Hello? Yeah, only one?
Just one.
Okay. Yeah.
So we were trying to distinguish between the resilience and the toughness.
Mhm.
My understanding was toughness is when material actually separate or break.
Yeah.
Okay, and then resilience, what kind of damage is that?
You're going to create permanent deformation.
Okay, but not necessarily.
Not necessarily breakage. Yeah.
Okay, perfect.
Okay? Yeah?
Thank you so much.
Okay. Hey.
Question
Yep.
about your slide. So I felt like you were saying strength versus maximum strength. What's the difference between ultimate compressive strength and ultimate tensile strength? Which one is strength?
Oh, so if you look at the curve, that's the maximum strength.
So
Okay,
this
the
at
highest
this point
point,
right
that's
here.
peak, yeah. And that's the ultimate strength.
At
Okay.
this point right here.
That's where breakage happens.
So what's the difference between maximum strength and ultimate compressive versus ultimate tensile?
Oh, it depends on the loading,
Okay.
right? So if you are loading it by tension, you will break it by tension.
Okay.
Yeah? But if you compress it,
So this can either be ultimate compressive or ultimate tensile.
yeah, but it will be reversed. It will be a mirror image because compressive stress are negative.
Oh, okay.
And the shape may not be exactly the
When you
mirror
say
image.
it would be opposite, it would be like this.
Yeah, it will be like a mirror image.
Okay, so this would be ultimate compressive, and this would be ultimate tensile.
That would be ultimate compressive, that's ultimate tensile. Okay, we're looking at tensile over here, positive.
Ultimate compressive.
And this one would be maximum.
And this is maximum.
This one is maximum tensile. That would be maximum compressive. Okay? All right. Hello. Yep.
So I just was like wondering, are this curve and these similarly related, or
Yeah, that's just part of this. This is total curve. And this one's just a small section.
that's looking at like this right here?
Yeah, somewhere around here.
Okay.
Okay.
And then could you explain? You mentioned something about like ultimate strength and maximum strength.
that's the maximum strength, because that's the highest point along the curve. Okay, and that's the ultimate strength. That's when things break.
That's like the breaking point
Yeah.
right here.
Okay, but it's lower on this curve because we are using the original cross section to calculate that. Yeah, I was going to explain this again.
Okay.
Because of necking. Yeah. Under plastic deformation, volume is conserved. So when you increase dimension in one direction, you're going to have to reduce dimension in the transverse direction because the volume is conserved. Yeah. We're having the same volume, it's increasing in the axial direction, so it needs to reduce in the transverse direction. So that's why we have necking. Yeah.
So where would necking be on?
So, oh no, beyond here.
Oh, beyond
The moment we produce plastic deformation, we're going to get necking. Right? Okay. So if we use a current cross section to calculate the current stress, the curve will keep on increasing. So in reality, the ultimate strength should be higher than anything else. Okay? Because at that point you have the smallest cross section. Yeah? But that's a sort of illusion. The stresses are reducing, but it's actually not. Okay? I'll try to explain that again. Okay?
Okay.
All right. Hey. Wow, you've got a lot of questions? Good. That means you're
So
thinking.
I was reviewing this last night. So I had a little bit of trouble with this one. Just tried this way until I figure it. It just was killing me last night. I couldn't wrap my head around
Well, that's creep.
creep.
Yeah.
Slow deformation.
That's right. Yeah, that's an example of creep.
So when you have like a heavy bank inertia, it'll eventually break.
Eventually it will break. Given enough time, it will break. Yeah. And you don't want to give it a jolt. It's also strain rate dependent.
A sealed crown is technically just replacing. It's giving enough time, right?
Sealed crown.
So like, or not a crown, a bridge.
A bridge. It depends on what material it's made of. Okay. Well, everything creeps. I'm sure you've seen a warped mill.
Yeah.
That's creep.
Okay.
All right. That's creep of the glass.
Alright. So what about the piston analogy then?
As you know, if you give it a jolt, you can break it. That's the plastic bag.
Yeah.
That's strain rate dependent. If you apply your force quickly, you're going to increase the stress.
Oh, okay.
Yeah.
Stress. So it's strain rate dependent, you said?
Yes.
So it's a quick amount of strain.
Yes. Yeah. Quick amount of strain, that'll give you a much higher stress.
Okay.
Then you can break the material. So it's like swimming. If you move slowly, the water affords very little resistance. If you try to paddle quickly, you get more force.
So is it kind of like, I don't know, it's like that material. It's like this little goop you made out of like borax or porcelain or like 6th grade. You slap it hard, it felt hard.
Yeah.
Okay.
Exactly.
Got it.
Okay. Okay, it's 10 past, so let's reconvene. Right, there are a few things I didn't quite explain clearly, and I missed something. The first thing is stress and strains have signs, okay? The convention is if it's a tensile stress, if it's a pulling, then it's positive. Okay? If it's compression, then it's negative. Yeah? And the other one is necking. Yeah? Under plastic deformation, the amount of material is conserved, or the volume is conserved. So if you extend something plastically, you're going to have to reduce the dimensions transversely, okay, in order to have the same amount of material. Otherwise, you will be created free material. Okay, we all want to do that, without any cost. But in reality, things will reduce in dimension in the transverse direction. So that's why when we come to, where are we? Now, okay. This curve, some of you are asking, why is the ultimate strength lower than the maximum strength? That's because the stresses are calculated using the original undeformed cross-section. Okay? If you account for necking, the reduction in cross-section, the stress will be actually higher once you go past the elastic limit. Yeah? And the actual stress-strain curve will be increasing continuously. So the ultimate strength will be higher. Well, there won't be maximum strength anymore. The ultimate strength will be the maximum strength. Is that okay? All right? Okay. So blame it on the engineers. I don't know why they use the original dimension. Okay. All right, moving on. Okay, I think I've explained those two. Right. So we've only covered the sort of typical stress-strain curve for metallic materials, which can deform elastically as well as plastically. But if you look at ceramics, they don't tend to deform plastically very much. Okay? Once you get to a critical stress, it will just break. So the stress-strain curve for ceramic material is a lot simpler. It's just a straight line. Yeah? For some other materials, you're going to have higher yield point or lower yield point. Okay? Higher maximum strength, lower maximum strength, etc., depending on the material. Bone is somewhere in between a brittle material and a ductile material. Okay? It's not completely brittle. Okay? It can deform plastically, but it doesn't have as much plasticity as a metal would. Okay? You don't want to build a strong structure with bone. Okay? Even though it works very well for human beings, yeah? Because we need to move about. Okay? We don't just carry load. Yeah? So if you want something that can really sustain a high load, then you don't want to build something out of bone. Okay? There are polymers which can give you very large deformation, but they don't tend to be very stiff. The Young's modulus tend to be low compared to all the other materials. Now, there are some materials that can remain elastic, okay, up to very high strains. These are shape memory alloys, okay, things that we use for orthodontic wires and the endo files. You can bend them to a very great extent, and if you look at the stress-strain curve, for a very long portion, the stress remains more or less constant. Okay? So that's very useful for orthodontic wires, because that means whatever you bend it, you know you're going to exert more or less the same force. And as your teeth move during your treatment, you can assure that the same force is still acting on the teeth, which is not the case for aligners. Right? Aligners are not made of shape memory alloys, okay, or material with super elasticity. Right, you can see that even though when you unload, okay, you can recover all the deformation, the unloading stress-strain path is not the same as the loading, okay? That's because during those deformation, there's a change in the crystal structure from one form to the other, and that requires energy, okay? So the energy expended during the loading and unloading cycle is the area within those two portions of the curves. Yeah? So the bigger that area, the more energy will be consumed, okay, by the deformation process, which can be useful if you want something that could really absorb an impact, say, right? Okay? Then you will like something with a big area in between. Yeah? But if you don't want that, okay, you don't want to spend too much work, okay, loading and unloading, then you want a small area in between. Okay, we've just mentioned impact. So traditionally, engineers like to use this so-called Sharpie test. So it uses a beam of material with a notch, okay, creating stress concentration. So we know exactly where the beam is going to break. And we use a pendulum, okay, raised to a great height, and just let it go, right? And the impact will break the beam specimens. And the energy required to break it can be calculated from the change in height, right? Okay. The height is a measure of potential energy. So if there's no change in energy, the pendulum will reach the same height, okay, as it first started, right? But if it breaks something in between, energy is going to be consumed. It will not reach the same height. So that difference in height will allow you to calculate the energy consumed by the specimen. Or you can do something simpler. You can just have a disc of your ceramic materials, okay, yeah, and you use a steel ball, again, raised to a really good height. Just drop the ball and see how high that ball needs to be to break that piece of specimen, okay? So again, the energy can be calculated from the height required to break the specimens. So knowing the impact strength of your material is obviously important, right? Okay, anyone plays hockey here? I'm surprised, this is Minnesota, come on. Or baseball. I'm sure some of you have played baseball, okay? Has anyone lost their teeth from playing baseball? Oh, did you raise your hand? All right, okay. So if you have a restoration, you want to minimize the risk of fracture from impact. You want to make sure that you have a resilient material with high impact strength, okay? Right, fatigue and endurance. Okay. Now, when I was a student, it's like 50 years ago, 70% of failure is caused by fatigue. Yeah? 70%. What do I mean by fatigue? Fatigue is failure caused by repeated or cyclic load that is well below the ultimate strength. Okay? I can keep bending my glasses. Okay? Eventually, it's going to break through fatigue. Yeah? I'm sure you've experienced that too, right? With other components. Right. Where was I? Oh, okay. Yeah. Nowadays, more than 90% of failure is caused by fatigue. So why is that? The reason was poor design. In the old days, we don't understand the materials as much as we do now. So the designs were poor, and a lot of those failure, the 30%, was caused by poor design, okay? Or accidental load that we don't have enough data, okay? But these days, we have accumulated a lot more knowledge about material behavior and how things are loaded, etc., and better designs with computers. So things don't break so easily from the start, okay? Has anyone tried to sell you sort of insurance for a refrigerator? Right? Those are scam, right? No one take them up anymore, okay? Because things are so good, they don't break easily, yeah? They usually come with a manufacturer's warranty, right? Okay? You don't need any additional insurance. If they can last the first year, they're going to last another 50 years or so, yeah? Right, but if we look at dental restorations, oh dear, okay. Yeah. I would guess, okay, at best, they are like engineering components 50 years ago, okay? 30% probably failed very shortly after placement, and the remainders are due to fatigue. All right, in theory, the number of cycles to failure depends only on the mean stress, okay? Because you can have tensile, then compressive, tensile, compressive, right? Or you can have purely tensile, okay, even though it's still repeating with changing magnitude, okay? The higher that mean strength or mean stress, the lower the number of cycles required to break something. And similarly for the stress amplitude, you can have very small stress amplitude, okay? Or you can have great stress amplitude. Okay? Either of those two things would shorten the life of your component. Yeah? So if you are designing for an anterior restoration compared to a posterior, which experience mostly compressive stresses, right? Or if you compare a cantilever bridge with an implant, single implant, the cantilever bridge would be experience tensile stresses, okay, more than compressive stresses. Yeah. So they will have different mean stress, and obviously they will have different stress amplitude as well. Yeah. And the number of cycles they go through will be different. Okay. The front teeth are mostly used for biting. Once you finish biting, the foot will be passed on to the posterior teeth for chewing. Okay? So the number of cycles they experience are also different. Yeah? Okay. So just summarizing what I've said, we can plot the stress amplitude against the number of cycles to failure. And you can see this sort of exponential reduction in the stress amplitude, right, against the number of cycles. Now, at some point, when the stress is so low, you will never get fatigue failure. Okay? Some materials have that sort of characteristic, and it would be nice to have that sort of materials. Okay? These are usually metallic. Yeah? So if you can design your restorations based on that so-called fatigue limit, if your stress, your operating stress is below that limit, you can be sure that your dental restoration is not going to fail through fatigue, okay? Assuming you get the loading right, yeah? But some materials do not have a fatigue limit, right? For metals, aluminum, or aluminium, where I came from, it doesn't have a fatigue limit. So any stress, whatever the amplitude, will cause fatigue eventually. Now for this sort of materials, we will put on a arbitrary large number of cycles for design. It's called the endurance limit, and they are usually in the millions. So for example, I want a restoration that will last 10 years. So you estimate the number of cycles of chewing that your patients would do, right? That would determine the number of cycles required to fail it. And then you back calculate, okay, and determine what sort of materials that you will need. All right? Okay? I'm sure that when you go out to practice, forget this, okay? I'll just put it on to see what happens. I'm going to get paid if I need to replace it anyway, so why bother? All right, hardness. Okay, this is important when you don't want to create any scratching or chipping. Yes? This one?
Yes, so for that value of stress, you can subject the load as many times as you want, and the material will not break.
It will not break.
Okay.
In theory, okay? But in practice, obviously materials would degrade. Yeah? Okay. There's a saying which goes, if you want something to break, put it into the mouth. Okay? Because you have mechanical loading from chewing, you have chemical challenge, acids produced by either soft drinks or bacteria. Okay? Moisture, right? All these would cause degradation of the material very quickly. Okay? Yeah. So that's just for guidance. Okay? Don't quote me. Okay. Hardness. Right. It's a compound property. Okay? How do you measure hardness? You take a very sharp indenter. Well, it doesn't have to be sharp. If you're measuring the hardness of metals, you can just use a ball, a hard metallic ball, and try to make an indent on the surface. Okay? So you put on a load, you wait for a while for things to settle, and then you unload it. Okay? Now, in the process, you need to make sure you have produced permanent deformation. Okay? Right? So it's basically loading and unloading beyond the elastic limit. Yeah? So it depends on what? Okay? The hardness is measured by the force required to produce that permanent indent. Okay? So it's force divided by the either projected area of that indent or the permanent depth that you create by that indentation. So it depends on everything that we covered. Depends on the stiffness, right? Okay, the stiffer the material, the harder you have to press on it, right? It depends on the elastic limit. Yeah, you have to bring it beyond or the yield point. Okay, so it's a compound property. Yeah, it depends on all these things that we've just covered. So usually, if you're measuring metals, you use this so-called Brinell or Brinell, okay, indenter. It's basically a sphere, okay. Or if you want to measure something more brittle, then you either use Vickers or Noob, okay. Yeah. For something that cracks easily, the Noob is better than the Vickers, okay, because you can limit the amount of fracture to a smaller extent. Because any fracture will skew the measurement of the projected area. So hardness, the measurement of hardness is related to wear resistance, okay, or abrasion, scratching or volume loss from a surface. Again, it's a compound property. It depends on the roughness, obviously, or friction. The hardness of the material we just mentioned. And it's actually quite difficult to completely replicate what's happening in the clinical situations when it comes to measuring wear. Typically, you get a lot of variations in your results, so you need a lot of samples, etc., unlike the stress strain curve, where it's very well defined. But we tried, okay? Isha mentioned that I'm the director of the Minnesota Dental Research Center for Biomaterials and Biomechanics. The MDRCBB was actually founded by my predecessor, Dr. Bill Douglas, okay, who was here for a long time. He and former chair, Dr. Ralph DeLong, co-invented this so-called chewing machine. Have you all been to the 16th floor? You've seen the marvelous chewing machine? Yes? Okay. We used to have 2 units. That's called Art 1, okay? That's called Art 2. That can do 2 body wear. That can do 3 body wear. The third body is the foot you put in between. Yeah? Well, according to some independent review, our machine is the only one that will satisfy the FDA regulation for testing dental materials, because it can accurately simulate both the forces and the displacement of chewing. Okay? It's built in the 80s. It's still running well. It's like a Rolls Royce. Yeah? Unlike your cell phone these days, you have to replace it every year. So here's an example of wear fasters produced by our Chi machine. Okay, it's a coated crown. Yeah, it's a stainless steel crown with a polymer coating on the outside to make it aesthetics. Yeah, but when we did this, all the data looked good. Yeah, we told the manufacturer, yeah, the material looks strong enough. Yeah, okay, go out and test it. It was a disaster. We got grilled a lot. And that's because we were applying the force at the wrong place. Yeah. When you put these crowns into kits, they like to do funny things. You know, they could be chewing on a pen. So it turns out that we should have applied the load on the cusp tips. Okay. Then we'll be able to simulate correctly the clinical situation. So whenever you do in vitro test, okay, just be careful. Okay, you can never completely 100% simulate the clinical situation. All right, good. We're getting there. Right. Viscoelasticity. You've seen the hysteresis curve for the shape memory alloy, right? Okay, that is some sort of viscous behavior, right? Which helps to dissipate energy. So some materials, especially polymers, they exhibit elastic as well as viscous behavior. And such behavior is time and strain rate dependent. So everything has a viscosity, yeah? So if you swim, you know when you move slowly, you don't get a lot of resistance from the water, right? Okay. But if you want to swim fast, you have to paddle like mad, right? And then you get a lot of reaction from the water, and you can move, okay? So that's strain rate dependent, yeah? So the stress is proportional to the strain rate. So here's another example, plastic bag, yeah? If it's too heavy, if you bought too much stuff, when you go into the supermarket, all these nice fruits, and nice biscuits, and you can't stop putting it into your bag, right? If you end up with too much stuff in your plastic bag, and you have to wait for a bus, okay, for a long time, the bag will start to sag. Okay. And that's creep, yeah, or viscoelastic behavior. And also, you don't want to give it a jolt, okay? You don't want to increase the strain rate, because then that will increase the stress, and it will break, okay? So you walk gingerly, yeah, like that. Okay, you have seen the linear spring for elastic behavior as an analog. You have seen the friction element as an analog for plasticity. For viscoelasticity, the analog would be a dashpot, okay, or a cylinder in a fluid. These are the bumpers in your car, which helps to dampen out any vibration. So if you plot the strain rate against the stress, you get a linear curve from water, that is. Okay. So that's called a Newtonian liquid or Newtonian material. But there are other sort of viscous behavior. This is shear thickening, right? The viscosity, which is the slope of the curve, increases with strain rate, right? The harder you paddle, the greater the force that you get. Okay, and the rate of increase also increases. Or you can get shear thinning. Can anyone tell me an example of a shear thinning material? I'm sure you eat fries with ketchup. You're going to say ketchup, right? Yeah, toothpaste, yes. I've never seen people shake their toothpaste, though. Right? But if you want the ketchup to flow out, you shake it. Yeah? Okay? You give it some strain rate, and the viscosity will come down, and the ketchup would flow out more easily. All right? Would be nice to have such a material to fill the cavity, isn't it? Actually, there is. Yeah. If you apply a strain rate to certain resin composite, it will flow. It will just flow into the cavity. Okay? But once you stop stirring it, and then it will become stiff again. That's a very nice property to have. Yeah. Where was I? Okay. Right. So typically there are two types of viscoelastic behavior. Creep, we've seen the plastic bags already. So if you apply a constant stress like gravity, okay, you can split the deformation into 3 stages. Primary creep. A lot of that is due to elastic behavior. Okay, some of it is due to viscous. And the secondary creep happens when you have a constant increase in strain as a value of time. Okay, so things will keep increasing in dimensions, even though you have not changed the load. Everything creeps. Okay, including a mirror. I'm sure you've seen some warped mirrors. Okay, that look funny when you look at the mirror. Yeah. So even glass can creep given enough time. Okay, but for dental materials, we're usually talking about much shorter time scale. So if we have too much creep, okay, a denture would deform to such a state that the patients can tell, oh, something is not right. Okay, right? Yeah, I would need a new one. Yeah. So you need to make sure that the denture material that you use have a good enough resistance against creep. You can always include some reinforcement, but that would be expensive. The other type of behavior, the previous one is called constant stress. Creep is under constant stress. If you just apply a displacement, okay, the resistance that you get from the material would reduce with time. Okay, that's called stress relaxation. You apply a load, not a load, a displacement. Okay, the resistance you get will reduce in time. So it's like an aligner. Yeah, you put on an aligner, you create a strained, controlled deformation. Yeah, that comes from the misalignment between the aligner and your teeth. You use that misalignment to try to move your teeth. Okay? But as your teeth move, okay, your teeth can creep too, right? Under stress, your teeth can move, create permanent deformation. They can creep. Or the aligner material can creep itself. So if your aligner material creeps too much, or its stress relaxes too much, then it won't be very effective. You're going to have to replace it very, very often. Right? Usually they last 1 or 2 weeks. Okay? Yeah. So not only stress relaxation can occur from tooth movement, it can also come from stress relaxation from the aligner material. Okay? So right now we're doing a lot of testing for different aligner companies to try to compare their force retention capability or their stress relaxation. Okay, well, that's all I've got. Okay, so I just want to remind you with this final slide, all materials contain elasticity, plasticity, and viscosity, okay, although to different extent. Right? And don't forget the design triangles, all right? Have a good day.